Okay, because it says in number one that it's a standard normal distribution, we could draw it out if we need to. 25th percentile, that's Q1. So somewhere over here is, the mark that there's 25% of the data to the left of that. And so the command you're going to need is in your calculator to figure that out. When you know the area or the proportion is 0.25, you're going to go to menu, 6, 5, 3. So 3 is the inverse normal there. So inverse normal is when you know the percentage or the area. It's always area of 1 underneath the curve. So if you know 25% of that would be 0.25 or 0.25. Because this is just a standardized score, a z-score, we're going to leave the default of 0 and 1 for the mean and standard deviation. Just say OK. And so we know that is, what is the z-score? Z equals negative 0.67. If I want to interpret that z-score, I would say that this value is 0.67 standard deviations below the mean. You want to say what direction you're going. In this case, we're below the mean, not above the mean. Okay, this one looks like another z-score type 1 here. So the weight of 2017 NFL quarterbacks is a mean of 222.9, standard deviation of 10.6. And it says Ben Roethlisberger has a weight of 240. So let's figure out his z-score. So this is for a z of Ben. I'm just going to call this Ben here. Z of Ben. And z-score. So it's the value, which is his actual weight, in this case, 240, minus the mean, which is 222.9, all divided by the standard deviation of 10.6. So in your calculator, you're going to type that in. So 240 minus 222.9 all over 10.6. We get positive 1.613. Okay. Z-score for the other guy is for Cam. Okay, so his weight was 320 minus the mean weight is 294 for his position over a standard deviation of 23.5 for his position. So we're doing their respective z-scores. And sometimes it's hard to tell just looking at it. Minus 294 over 23.5. We get a z-score of 1.1. So Cam is 1.106 above the mean. Ben is 1.613 above the mean. So which player, relative to his position, we would say that Ben Roethlisberger is heavier relative to his position he plays in football. Golf scores from the Sandra Pitts Invitational can be modeled by a uniform distribution. Uniform, so that means the graph's going to look like this. It has a flat top to it. So it's a rectangle, at least it should be a rectangle. It goes from 41 to 50, 41 over here to 50. So that's a distance there of 9. So a length, essentially, of 9. We know the area of that guy is 1. So how tall it is. If the length is 9, what's that? So area equals length times width. So we would say 1 equals 9 times the width. And so we get the width is 1/9. Width equals 1/9. What was the question now? So that's 1/9. All golfers that scored 43 or below get recognized. What percent of the golfers are recognized? So 43 looks like, I don't know, somewhere around there. And so we get 43. That's a distance there of 2 units. So 2 units between there and there. And we want to find the area of that. What's the proportion? So whatever 2 times 1/9 is, or 2/9. If you want to get that as a decimal, you would need your calculator and you just type in 2 divided by 9, put a decimal point or control enter, and you get 0.222 repeating. What percent? 22.2%. Karen was in the 20th percentile. Okay, so it looks like there's 15 students, so 20th percentile. So what is 0.2 times 15? So 0.2 times 15 is 3. So there are 3 students that are worse than, oh, are these in order? That's so nice, right? So there are 3 students that are below the student score. And so Karen must have scored a 78. She scored, you want to enter that as a sentence. I'm not going to write it out here. It's too hard for me to do that. But Karen scored a 78 on the statistics test or exam. And there were, if you want to interpret the percentile, she was better than 20% of the students who took the exam. Density curve below, so what are they? So I'll say C can't be the median because if you look, half the data is not to the right and left of that one. It's probably the mode. So I would say that the C is the mode. B, however, does look like about half is over here and about half is to the left of that. So it looks pretty equal to me, or at least could be equal. So that's the median. That's when half, you want to just know that if you don't, write that down if you don't know it. Half the data is to the right, half the data is to the left of the median, which means A is the one that's left. Well, that gets pulled with the skew, right? So this is left skewed. So that line right there is for the furthest left. That has to be the okay. So choice here. Okay, the mean and standard deviation are approximately what? So right away you can see the mean is definitely 200. So I think we can cross out A and B. It's not one of those guys. I know that 99.7% of the data is within 3 standard deviations in each direction, actually. But so if you look at this number, it must be 3 standard deviations. We're pretty close to 3 standard deviations out. Well, 200 is the mean. So what's the difference? If there's 3 equal standard deviations between 200 and 400. It's going to be the distance of that, which is 200, divided by 3, because there's 3 equal standard deviations. Whatever 200 divided by 3 is, I think the closest answer would have to be 67. So it's got to be C. In other words, z-scores always have a mean of 0, a standard deviation of 1. If you draw it, middle is 0, 1, negative 1, 2, negative 2. Scores on a university examination are normally distributed with a mean of 62. So 62. Standard deviation of 11 would be 73. 84. 5. Writing. 53. Right. Yeah. 51. 51. And the last one out there, 3 standard deviations below would be 29. If the bottom 5% of students will fail the course, what is the lowest mark that a student can have and still be awarded a passing grade? So 5%, we know that 95% of the data is within 2 standard deviations. So that means there's 2.5% to the left of 40 there, but they need 5%. So it's somewhere in here. I don't know where. So we've got to use our command here, right? So we go to that same command we used to start the day. So again, we're going to go back to the inverse norm command. So menu 653. In this case, we want, it always, inverse norm always works to the left. So what percentage do you want to the left? In this case, we want the bottom 5%, so 0.05. The mean is 62. The standard deviation was 11. And so 43, 43.9, so 43.9, probably 44 will be awarding a passing grade, basically. Okay. A company produces ceramic floor tiles. They're supposed to have a surface area of 16 square inches. Due to variability, the actual forms a normal distribution. So when it says that, you always want to just sketch it out, right? So kind of sketch it out, okay. In the middle is 16.1, standard deviation of 0.2, so this is 16.3, 16.5, and 16.7 going this way. Always just go 3 standard deviations. We do that in both directions, so 15.9, 15, put a little sloppy here, sorry, 0.7 and 15.5. Okay, what proportion of tiles are less than 16? So 16 is like right in here. So we want all of this and shaded to the left, right? So we want it 16 or less. So in this case, we're going to use our calculator again, but we're not going to use inverse norm. We're going to use the norm CDF. So menu 6.5 and 2 is norm CDF. And so the default is negative infinity, which is what we want here. And the upper bound is going to be 16. And then the mean is 16.1. Standard deviation is 0.2. And so we get 0.308. 0.308. By the way, so you would want to say, 30.8%. Well, that's the answer. If they were saying this, if you wanted to show your work, typically what we like to see is something like this. You'd write norm CDF. You'd write negative infinity, just like you typed in your calculator. I'm actually copying from the calculator right here. 16.1, comma 0.2, it's a 0.2. And then you label these. This is lower, upper, and you write a little neater than this, mean, standard deviation. So you kind of label what those things are. That's considered showing work for this problem. So if you do that, the sketch also helps. We like to see both those things. This is multiple choice, so you're getting graded whether you know it or not. But if you show some work, even if you got the wrong answer, if you showed the work and the work was right or something, or work had some good qualities to it, sometimes you get some partial credit there. Even on a multiple choice, I'll do that sometimes. Which of the following dot plots would best be approximated by normal distribution? So you can see this first one is skewed right. You can see if definitely skewed right. This one's kind of bimodal or multimodal. It's kind of, got not quite uniform there, but too many modes there. Skewed right for sure. This one looks somewhat uniform. Do you see how the top is somewhat uniform there? This one is the only one that looks somewhat approximately normal. We always say the word approximately normal, not exactly normal or something. 45 golfers from a tournament. Okay, looks skewed left to me. Hannah shot a 74. What percentile? What was her percentile? And then interpret the percentile. So I didn't say that very nicely there. Okay, so 74. So she shot 74. So 74 is right here. So how many people did she beat? There was 45 golfers. She wait a second. Actually, she beat almost everybody. There's one person she didn't beat, right? So in this case, we're going to say what percentile. So you actually, here's what's weird. If you're taking a test, you want to be in the top percentile. But if you're in a golf tournament, you want to be in the lowest percentile, actually, that you can possibly be, like 1 percentile or something, because you want to have the lowest score. So 74 is actually a very good score in this tournament. We don't want to be the highest percentile in this particular case when you're talking about golf score, because we want a low score. So what percentile is it? There's 1 out of 45. So you would type that in your calculator. So 1 divided by 45. So 2.2%. So the percentile is 2.2% or 0.022. And interpret this. So Hannah's score was higher than all but 2.2% of the golf tournament participants. Her golf score was. Okay, so find and interpret the z-score. So what is her z-score? So z equals her score, which is 74, minus the mean, which was 82.422, all over the standard deviation, which is 4.1805. So I would just type that in your calculator just like that to get the z-score. It's probably going to be a negative score. Let's see. So we get 74 minus 82.422 all over 4.18052. So her z-score was negative 2.01, blah, blah, blah. So she was 2.01 standard deviations. Her score was 2.01 standard deviations below the mean. By the way, anything more than 2 standard deviations below the mean is highly unusual. In this case, an excellent score on a golf tournament. In the same day, but at a different course, at another golf course tournament, at maybe an easier course, and that tournament, the mean score was 77 and the standard deviation was 5. One of Hannah's rivals, Sophie, had a score of 72. Relatively speaking, who had the better golf score, Hannah or Sophie, in their respective tournament? So this is, I'm just going to kind of put here, this is Hannah's score, that's her z-score was this. So let's figure out the z-score for Sophie. Okay, so this is going to be, her score was, let's see, she had a 72. 72 minus 77, all over standard deviation of 5. Okay, so let's figure out her z-score. So it seems like she did better, right? 72 minus 77 all over 5. And you get negative 1. Ooh, negative 1. She's only 1 standard deviation below the mean. By the way, this is negative. I forgot to put that. She was only 1 standard deviation. Hannah was 2 standard deviations below the mean. So Hannah had the better score in her respective tournament, even though her score wasn't as low as Sophie's score. But it must have been a tougher course, and compared to the people she played against, she did better. 200 songs recorded by the Rolling Stones. They have the mean of 4.23, standard deviation of that. So we're want to express the time rather than minutes. Find the mean and standard deviation. So we don't need to draw a normal curve. We don't need to do norm CDF for this. We're doing a conversion here. So he wants to express the time in seconds rather than minutes. So we have to convert. So let's talk about what happens when you do conversion. In this case, converting, let's think about it. If we want to convert to seconds rather than minutes, we're going to, so this is in minutes, so we're going to multiply the minutes by 60, right? So when you multiply something by 60, let's take the mean. So the mean, the original mean, I'm just going to put original there, was 4.23. The mean, the new mean, this is the new mean, is going to be, so what's affected? When you multiply by 60, does that affect the new mean? Right, it was 4.23 minutes, now it'll be, I guess, right, 4.23 times 60, 253.8 seconds, right? So now, so we do, to convert, we're going to do 4.23, and I would show this work times 60 equals 253.8 seconds. Make sure to put that units there, especially on a question like this where about the units. Let's talk about standard deviation. So multiplying does affect the mean, right? The measures of center are all affected when you multiply every data value. But standard deviation, will that be affected by multiplying? Let's see. If you add, it doesn't affect standard deviation, but if you multiply, it does. So you're going to need to take 1.38 times 60. It is going to be more spread out. So you would say standard deviation equals 1.38 times 60. So the new standard deviation is 82.8 seconds. Study of elite distance runners. I found a mean body weight. So we're supposed to draw this, right? So we've got the normal curve there, approximately normal 63.1 in the middle. And 4.8. To do this in your calculator, I like to do this. So you type in the number 63.1, press enter, plus the standard deviation at 4.8. So plus 4.8. Press enter 3 times. So that just does all the math for you. This is 67.9. 72.7, and 77.5. And then when you do it the other way, so you type in 63.1, press enter, subtract 4.8, and you get 58.3, 53.5, 48.7. Use the empirical rule to find the proportion of runners whose weight is between 48.7 and 67.9. Because it says this, I don't really want you using norm CDF on this one. I mean, if they didn't say that, norm CDF is the way to go, 100%. But there, remember what we're saying, that within one standard deviation, that's between here and here, 68% of the data. So there's 34% right between those two, right? If you do 95 minus 68, because 95 is 2 standard deviations. That's 2 standard deviations. Minus that is 727. Divide that by 2, you get 13.5. So this is 13.5% between those two. I haven't actually answered the question yet. 13.5. If you take the 3 standard deviations out, which is 99.7, you need to memorize those numbers. Minus 95 is 4.7, divided by 2 is 2.35. So right in there is 2.35. If you're 50% to the right, you're missing a 0.15% right there. That's in that last little part. And again, 2.35% and 0.15% in the very past 3 standard deviations below. Okay, so we want between 48.7, that's this guy, and 67.9, that's this one. So we need the 2, let's just add them up in our calculator here. We need the 2.35 plus 13.5 plus 34 plus all the way to 34. 83.85, and I would show that work. So if you want to show the work, so I know you did it this way. Plus, you'll get a more exact answer if you use norm CDF. So I kind of know you did that because we want the approximate answer that you get by using the empirical rule. Sorry, plus that equals 83.85%. What proportion of runners have weights below 60? So below 60. Now, see, they didn't use the empirical rule because 60 doesn't fall on a nice thing. It's like between those two guys, right? So you're going to use your norm CDF command. So menu 652. It defaults to negative infinity, which is what you want. We want 60 and below. So 60, mean is 63.1. Standard deviation is, I forget what it said. Oh, I'm sorry. That's 63. Yeah, with it 4.8, standard deviation of 4.8. Sorry, I forgot which part of the question, which question we're asking. And say okay. And so 20.259. So 0.259. I'm okay if you write it as a decimal or 25.9%. It's good to write it as a sentence. 25.9% of the runners have body weights below 60 kilograms. What proportion of runners have weights above 70? So again, we're using norm CDF. So menu 652. In this case, the 70 is the lowest, right? The top mark is infinity. So if you hit the pi key and go over to infinity, and then the mean was 63.1. Standard deviation was 4.8. Keep forgetting that one. Okay, so we get 7.5, so 0.075 kilograms. What proportion? 7.5% essentially of runners have body weight above 70 kilograms. Calculate and interpret the 45th percentile. So you're kind of like, if you think about it, like you're doing 45th percentile. So 45% of the runners. So you're shading the left there. So we want to go menu, 653 is the inverse normal. We want to the left is 0.45. And we're going to say what those things are, if I can remember those. 63.1 and 4.8. We get 62.49, or about 62.5. 62.5. Interpret the 45th. So interpret that. So 62.5. So the person who weighs 62.5 kilograms is heavier than 45% of the runners that were in this race. Okay, last one. So 20 students were asked to guess the age of a man in a photograph. Here are the guesses. Are these approximately normal distributed? So we're supposed to use two ways of doing this. So one way is use an empirical rule. Another one's draw a graph. So let's just type in our data into our calculator first. So you go up here and this is age, I guess, so ages. Type in the order they appear in here. Okay, I think I typed in all 20. That sounds right. I always like to check to see I have the right amount of them. I'm going to hit the home key and go to data statistics and just choose age. Okay, so the three things you're looking for when you're looking at the graph, you want to say something about, is it approximately symmetric? I would say yes, approximately symmetric. Is it unimodal? I would definitely say it's unimodal. And then is it bell-shaped? And being pretty generous, there's not that many points, so it's hard to say bell-shaped, but it seems approximately bell-shaped. Now use the empirical rule to do this. So this is where it might help to be able to look at the data all in order. So I'm going to go back to the page here. Sorry. So if you hit Control left arrow to go back to the Listen Spreadsheet page, I'm actually going to do this. I'm going to add a calculator page. I'm going to show you something. If you didn't know this, you can do this. You can also do this by hand. It's not a big deal. If you type in the command sort A, sort ascending is what that stands for. Sort A of the list, the title is called age. Now when I look back at that list on page 1.2, they're definitely ordered from smallest to biggest. And you kind of see it, right? You see the first one is 33. If you did it by hand, you'd get this as well. But I'm just trying to tell you a way to get your calculator to do it. So now they're organized from smallest to biggest, which really to this next part, you almost need that. You need it kind of organized in that way. Okay, I'm going to figure out what one standard deviation is for this data. So to do that, I need to figure out the mean and standard deviation, right? So if you go to menu 611, we're going to do one variable stats, choose age, it's the only one I have, and it's going to give us two things. So it tells us that the mean, X bar, is 42.75, and the standard deviation, which this is a sample, so I'm going to take SX, sample standard deviation, which is 4.15331. Okay, so I want to go out one standard deviation each direction. So to do that, what I do is I type in the 42.75 plus one standard deviation, right, would be 4.15331. And we also subtract that number. So I'm copying and pasting, mouse up, 2 clicks, press enter. So I need all the data values between, so this is like mean plus or minus standard deviation, right, is going to be these two numbers. So 38.5, and between the other number is 46.9. Okay, so if you look at the data, so I'm going back, control left arrow, I have them all organized by, so if I go to the first 38.5. So the first three, there are three there that are too low. They don't fit in that range. If you go to the higher end here, 46.9. So right there, 48, 49, and 50, there are three that are too high. So we have 6 out of, I believe, 20 that are not in the range, which means, I guess we actually have 14 out of 20 in the range. So let's go back to our calculator page. So 14 divided by 20 is how many are within one standard deviation? Is 0.70. So again, so within one standard deviation, so this is 14 over 20 is 0.7. So that within one standard deviation. Okay, so if we do that again, so we go back up here and go 2 standard deviations. So I'm doing that 4.15 times 2. And I'm doing that 4.15 times 2. So now we're going a 2 standard mean plus or minus 2 standard deviations is between 34.4 and 51.05. So now look back at your data. Again, I like to look at the data that's either been organized in your paper or not. So 33 is still too low. So there's one that's lower. Whoops. Oops, sorry about that. And 51.05. There's none that are higher, right? So we actually have 19 out of 20 that are between those two numbers. So if you get your calculator page out, 19 divided by 20.95. Ooh, I like that, right? So within 2, so this is 0.95. That's actually perfect. That's within 2 standard deviations. You want to show this work. That was mean plus or minus, so you get those two numbers, and then mean plus or minus 3 standard deviations. If you just mouse up and copy and paste that command and go 3 instead of 2, 3 instead of 2. So between 30.29 and 55.2. So let's see if that smallest number is below or still in the range. 33 is bigger than that, so all the numbers. So 20 out of 20, which is 100%, which is pretty darn close to 99.7. So using the empirical rule, I would say yes, and I would make this a sentence, yes, because we got one standard deviation was 70%, which is pretty close to 68. 2 standard deviations was exactly 95, which is perfect. And 3 standard deviations, 100%, which is pretty darn close to 199.7. So this definitely passes the test. We can say this data is approximately normal. And again, you've got the answers here if you need to scroll. It's written a little neater than I wrote them on your review sheet there. So just kind of scrolling through those if you need to stop it.